Right. So one of these points, I thought we were going to go up there to decomposition, but we've actually gone down to the bottom here. Pattern recognition. Do we see a pattern? If we see something that's a pattern, we mean something that's repeated. If something's repeated, then maybe we can build a general purpose little function that we can just plug in. We call them parameters, and it puts out a nice solution for us. That's the idea of pattern recognition. Let's look at that. So there it is diagrammatically, the idea here. So we see this repeating pattern here, right? So this thing seems to keep happening. The shape here of these dominoes. So if we saw that was happening all the time, then maybe we could do something to solve this, and then we could use it over and over again. So that's what we mean by pattern recognition. It's one of the 4 major components of computational thinking. So there we go. I thought we would start with decomposition, but we're starting here with pattern recognition. That's fine. So a pattern, as it says, regular way something happens or is done. The example that we used as pattern recognition in one of the earlier lectures, remember, as I said, was the L-shaped blocks, right? And what was the pattern? We came up with y is equal to 2x plus 1. So a pattern can be represented in sequence. Here's some other ones that maybe you can see the pattern here. So what we normally do when we look for a pattern in a bunch of numbers is we say, okay, well, what's the difference between these two numbers? Oh, the difference is 4. So the pattern is, every time we just add 4, right? X plus 4. And what's the difference in these ones? Oh, well, look, this number seems to be 3 times that number. This number is 3 times that number. So it's just X multiplied by 3, the number before multiplied by 3. And this one is a special one. This one's called the Fibonacci series. So basically what it is just take 2 numbers and add them together. So these 2 numbers added together is that. Then these 2 numbers added together is that. See the pattern? Then these 2 numbers added together is that. A Fibonacci series. So each one of those is a pattern, and you could solve that. There is a little computer program that you could write for each of these. Very simple little function that you could do for each of those, including the Fibonacci series, which was designed first, discovered, I guess you'd say, by a mathematician by the name of Fibonacci. So found the pattern. We like patterns. So for example, we actually put patterns into our clothes. And one of the things that we talked about in an earlier lecture was the Jacquard Loom. And so the Jacquard Loom is using these special sort of, I don't know, they're bits of wood or something, but they have holes in them that are in a pattern. And the pattern of the holes was used to program the loom so that the right strings were pulled down at the right time. And so using something like that, you could get a very accurate development of a pattern, something like this, which would be highly desired by people would put that as clothing that they would wear or whatever. And so that machine, as we talked about in maybe our first lecture or second lecture, was developed way back in 1804, like 200 years ago. Here's a pattern. And so what's happening here is the company is every time somebody buys something from them, the company produces this piece of paper, and the piece of paper has some details on it. So it's got items, and then the items and a quantity and a price for each item. And then, the quantity times the unit price gives a total. Then at the bottom, you've got some other subtotal of all of that. Then maybe there's some tax that you need to add or a discount. There's a discount there. And then maybe there's some tax. And then there's an amount that's paid. So somebody's made this. We call it a template. Every time somebody sells something, they use the same bit of paper. It's very easy for them in their accounting system to sort of pull out the numbers that are important. And it's also very easy for their customers to see the numbers that are important to them, right? So how many of this unit did I buy, et cetera, and what did I pay for that? What was my discount? Did I get a discount on individual items, or was a discount an overall discount? Does that discount, is that in accordance with the agreements that I have with the company? Stuff like that. So basically, we're just getting a lot of information presented in a way which is very easy to understand by the customer and by the by the business because it's standardized, right? We do it the same way every time. Makes it fast. I mean, we know exactly where we want to look. Maybe the only number we care about is this one, but maybe we care about some other numbers. But the thing is, we'll find those numbers in the same place every time. Standardized. So that is a pattern that we use that really helps us to do things in our business faster. So it is a critical step. If we can see a pattern in the way things are working in our business, then maybe that pattern could be susceptible to us writing a little module to treating it as a sub problem that we can sort of speed up by making it automated. So as it says, there's two different types of patterns that we might come across: patterns that occur across problems and patterns that occur within a particular problem. Okay, I don't have any notes on that, but yeah. Why would we look at patterns? Well, we want to solve problems, right? We use every way that we have, every tool that we have to help us solve our problems. And if we can, I think the reason we look for patterns is because, as I said, we can standardize. If you can standardize it, then maybe you can make a little computer module to do that. Then you can speed things up, because that's the power of computing. Computers can do the same thing over and over again very, very fast, like producing those pattern, the Jacquard Loom. We could do that much faster than a human could do it. We can produce those receipts much faster than a human could do it with the computer. And so if we see something that's standard and that is done the same way every time, yeah, repeat. Use a computer to make it faster. So I think that's all we need to say about that. Patterns that occur across problems. So that means a pattern which is sort of a general pattern that's everybody's going to have. So this one here is a pattern about the athlete wants to know what is their average, their time. And so they run the same distance, and maybe they run that distance 10 times. What was their average time? The meteorologist wants to know what is the average temperature. But the meteorologist is actually taking that temperature like every hour of every day in the year. So it's a lot more temperatures. But the pattern that we see is that we get these numbers and we find the average. And the average pattern is the same wherever you do with it, right? You take the total and you divide by the count. That's average. And so that's a type of a problem which goes across, can be solved everywhere. So we should have a computer program to solve that, and we do. So I mean, if you open up your Excel spreadsheet, you'll notice there, if you put a bunch of numbers down, you can calculate the average just by pulling down a button. There's average, because we know that that's something that we want a lot of, right? We want to know the average. We want to know the average temperature. We want to know our average GPA. We want to know our average time. We want to know the average of lots of things. And so that's a general problem, which, as it says here, it's a pattern. It could be discussed as a pattern across many problems. And so we have little widgets and programs and modules to sort of solve that. So what about a pattern inside a problem? Useful to minimize the amount of code. So if we see that, well, what's this one doing? Customer wants a mobile application will allow them to register their account. Restaurant owner needs to register and in order to create their account. Drivers need accounts as well. So within this organization, which is a restaurant, we've got multiple accounts. So maybe there's something similar about those problems of registering the accounts. So maybe we could write an account registration module, and then the customers, the drivers, the owner could all use that module and just put in different inputs, but everybody would get a profile out of it. You guys have done lots of registrations online with different things, I'm sure, and you probably noticed that they all have something similar. So maybe somebody has written a general purpose profile adding module that people kind of borrow. Here's a nice one, which is maybe we want to draw different shapes. We could spend a lot of time and write a different module to draw each of these shapes. But if you thought about it carefully, you might be able to write one module which draws any one of those shapes. And so basically what that module would have to do would say, go a certain distance, then turn by a certain angle, and then do that again until you get back to the point where you started. And that could be general, right? Now, depending on what the angle was, if you had an angle here, where the three angles added up to 180 degrees, that would be a triangle. If you had an angle where the three angles added up to 360 degrees, you're going to get the quadrilateral and difference. So just based on the angles and the distances, you could get different shapes. Then also you could fill in the color just by specifying that. Now this, as it says, it's a nice. There is a nice little note. First time we get a note at the bottom of our slides is this is actually, no, it doesn't. Yes, this is actually used in object-oriented programming. So our more modern programming languages, Python's one of them, Java, are object-oriented. You would create an object called shape, and then you would have attributes associated with that object, which would be, for example, the length of the side, the angle, and the color. And then just using that, you could create a new object anytime you wanted, just putting in as inputs the length of the sides, the angles, and the colors, and you'd get your shape. So object-oriented programming definitely takes up on this sort of concept of patterns. Object-oriented programming is our modern programming. You'll be doing that definitely by your second year in your Python class or your JavaScript class. You'll be doing object-oriented. Hooray for that. So maybe you can see patterns here. So now we're getting into some notes at the bottom. Please do look at the notes on the bottom there, but maybe you can see a pattern there. So basically the pattern that I hope that you can see is that everything seems to be a circle or a subset of a circle, right? You know, so basically we just got some circles here for the eyes and pupils, a circle for the face, a semicircle arc for the mouth. Everything's a circle. So we could do this with objects, right? So the object could be a circle, and we just specify some certain things about that circle, right? So for example, what is the center point of that circle, which could be a coordinate on a two-dimensional graph, right? Coordinate X and Y, where is the center? Then you could have the diameter of the circle. Then you could have the thickness of the circumference line. So where's the center? What is the diameter? How far out? And then how thick is it? And from that, you could draw all of these circles. And so one little module, which could be my circle drawing module, from that, I could make this little diagram with using one little module multiple times. Now, one of these circles, I would have to use some kind of a fraction there for the actual circumference. I mean, I'd still have the center, and I'd still have the circumference, and I'd still have the width, but I would do my drawing to only be half of it. And then I get that little shape. So very easy to apply that in a computer using an object-oriented language, which you guys will become familiar with later. So yeah, as it says, what do we need? You need to know the diameter, which is the distance from the center of the circle. Well, it's actually across, right? Distance from the center of the circle out is the radius. Diameter is 2 times the radius. The color of the line, the fill color, and the size of the cut. The size of the cut is how far do we go around the circumference. And am I missing anything? There's some notes there. I wanted to make sure I don't miss the notes. Can you see those down there? I hope I'm sharing this. Yeah, I'm sharing this. This is a fundamental idea behind classes. Yes, class, you would have an object, and the classes which would relate to it could relate to these attributes. All right. Or a class could be the circle. Look at this. There's shapes there that are patterns that could be reproduced over and over again, could be coded quite simply. So we got circles. We've got circles that are divided by lines. We've got squares, which are also divided by lines. We've got a rectangle, a couple of rectangles, and we got a triangle, another circle with a bunch of triangles. You could actually make this tree up by just overlapping a bunch of filled up circles, right? I hope you can see that, right? So you can put a circle here, you can put a circle here, circle here, circle here. We just overlap them so that there's no gaps between them. Then we got another rectangle. So, I mean, all of this could be drawn just using circles, triangles, and lines, and rectangles, yeah, and squares. So, I mean, you could make little programs for each of those, put them together, and start drawing like that. If you like drawing like that, I don't know, maybe you don't. So, for example, you would have a module for a rectangle. You need to know the width, the height, the border, and the fill. From that, you could draw the house, you could draw the door, you could draw the tree trunk. Then you need the circle, which would be the diameter, border, and the fill. From that, you could draw this window, you could draw the sun, and you could draw the tree leaves. Then the triangle, you know how to do a triangle. You need to have the length, the angle of the triangle, three angles, border, fill, and the rotation. So then you'd draw this. And you'd also need the rotation for these triangles to get them oriented right. So with those three modules, each of those could be a class in an object-oriented language. And those, then you could go ahead and you could draw something like this. Okay. Okay, so supposing you had a scene like that and you wanted to reproduce it on a computer in a simple way. I mean, it's like grade 2 student way, isn't it? But, you know, we're going to do it with a computer. What you would do is you'd look at the scene that you wanted, you would break it down and say, where do I need a rectangle? Where do I need a circle? Where do I need a line? And you do each of those individually. And that's what we mean by subroutines. So here we got a subroutine, which is the subroutine draw a circle. The stuff inside the brackets are the inputs. We refer to those as parameters. Is there another name we use for those? Okay, be careful on this. I saw this in a quiz last semester. The quiz was, you know, what do we call the inputs into a module? And the answer is we call them parameters. But in the quiz, it said arguments. If you see the word argument and you see the word parameters, they're the same, okay? Arguments, parameters. So don't get fooled by that. Anyway, so here's our arguments or our parameters. And so we got some numbers there. They're going to represent the actual center of the circle. What is its coordinates? 3 centimeters, I guess, would be our diameter. Black would be the color of the circumference. I guess whether or not there's a fill. This one doesn't have a fill. And how thick? I guess something like that. Actually, no, the 50% suggests that that's how opaque it is or whatever. Yeah, anyways, not sure. Go through that and look at it if you like. So a subroutine, I also refer to that sometimes as a function. Subroutine is going to be something that you could use over and over again, a repeated little process that is part of a bigger process. So definitely the drawing a circle would be a subroutine. We could draw polygons, as it says, with subroutines. I think that if you go back to this one here, each of these could be considered a subroutine. Could also be considered an object. So I think that's fine for that. Working backwards. The idea of working backwards means that before we try and finish solving the problem, we absolutely know where we're going to finish, what it looks like when we're done. If we know what it looks like when we're done, we can sort of work backwards from that. We could use that in our trying to get to the place where we're going to go with our friends for dinner. But we could also do it for drawing our diagrams as we've done today. I don't know how you're feeling about that. I'm not going to go through all of that. I've basically said it. Basically, it's just about we know what we're going to look like when we're done, or where we know when we've achieved our goal. What would it look like when we're almost achieved our goal? You know, 90% achieved. Then what would we have to do to get from that to our goal? Then what would it look like when we're 80% achieved our goal? And then what would it take to get from 80% to 90%? That kind of idea. That's what we mean by working backwards. Last slide, hooray. And there's some notes on the bottom there. So the notes on the bottom is to be aware that there's a difference between recognizing a pattern and that sort of goes over and recognizing a smaller pattern within. So can we recognize a cat? Can a computer recognize a cat from a photo? Yeah, maybe, probably. And so what it would do is measure the distance between the eyes, measure the shape, the distance between the eyes and the nose, sort of measure basically by distance of things that it can recognize in the picture. It would be able to recognize that that's a cat, not a person. And likewise for these photos here, it would do the same kind of thing, right? What's the difference between the eyes compared to the nose, compared to the mouth, compared to the shape of the face? From that, we can see that that's not a cat, right? That's a person. And so, is anybody doing this? Well, yeah. There is facial recognition on the streets of London and in, I think, every Chinese city. And, maybe one day soon it'll be here as well. That's very useful for authorities because they can go back. Okay, so there was a demonstration and, people were there. Well, who was there? Oh, there was people. Or how many? That would be our pattern recognition, that we know how many people were there, right? Just get it from that. Now, let's suppose we want to know, was this individual there? So we want to know that when we turn on our phone, right? I turn on my phone, I could use my finger, or it looks at something in my face and says, is that me? You've got that on your phone if you've got an Android. Probably you have it if you have an iPhone as well. So what's it going to do is it's going to measure very, very specific sort of things, because things where we differ, so that my face is different than your face. Even though as I get older, my face changed, but there's some things that stayed the same, right? The distance between here and here, the distance between here and here, maybe this distance didn't change, it didn't stay the same, but some distances stayed the same. And from that, it can know that it's me and it's not you, right? And so, and you might say, well, today's sunny, today's cloudy, my face looks different. Yeah, but the distance between your eyeballs is the same, right? And the distance between the tip of your nose and your eye is the same. And it's different than that person. And so we know it's you. So yeah, that could be your facial recognition, which again, if you went out in the streets in China, that system is working. Now, even if it doesn't work yet, I read something was like, this was like 8 years ago. If you step out in the streets of London, so we call it the City of London. The City of London is kind of almost like an island downtown. That's where all the rich people in London are. The City of London is where they have all of their big banks. All right. And so the City of London, if you're walking out in there, they say a person walking around in the City of London is on video recorder on closer TV. Like 300 times a day. So, I mean, gee, that's a lot of video, right? Now, supposing they don't have facial recognition, but what they have is they've recorded all of that, right? And keeping stuff, recorded stuff is cheap now. It's way cheaper than it used to be. I mean, you can have 20 terabytes on a USB now. I saw that on the weekend. I couldn't believe it. 20 terabytes. That's a huge amount of data on a USB. Now, that's not cheap, but it's not terribly expensive. So what I'm saying is they don't have to throw away any of that video. I mean, that video is there. They don't have to throw it away. 10 years from now, when it's really, we've really fixed up this pattern recognition sort of thing of individual faces. Yeah, they could go back and say, oh, well, something happened. Somebody has a controversy. Something happened in London. They didn't like it. And they say, oh, Mark, you were there. And I say, no, it wasn't. They say, oh, well, we'll go back through this. And of course, our computers are really fast and strong. They do their pattern recognition. There you are. You were there 10 years ago. You were there. Now you have to go and talk to so-and-so because of that. So, yeah, I don't know if you think that's good or not, but that's where we are. I think I'm done now, unless there's some questions. So what I'm going to do is I'm going to stop the recording. And I'll be here for a few minutes.